Okay, so today we're going to go over 10.3, depending on the book. If this is the Stewart book, it'll be 11.2. But in Briggs, it's 10.3. But basically, we're going to kind of intro series, and then this is going to be a little bit of a longer video. We're going to talk about geometric series and telescoping series. So this will be, you know, a good 30 or 40-minute video, I believe. So let's suppose that we have a sequence A sub 1, A sub 2, A sub 3, A sub 4. We want to take a look at the addition of that sequence. So we could add up all those terms, A sub 1 plus A sub 2 plus A sub 3 plus A sub 4, so on and so on, right? So this leads us to this notation, oftentimes sigma notation. I just call this a series, where this is usually referred to as the index. Okay, and it tells you where to start. So this is your starting point, and this is your ending point. Now the problem is you can't end at infinity because it goes on forever. So this lies the difficulty with a series. So the way I was taught is that any sum that is finite technically isn't a series. It's called a partial sum. Whenever you're using the word series, normally you mean an infinite series. But, you know, it's kind of a gray area. The way I was taught is that it is a series if you're approaching infinity. So otherwise, it's just a partial sum. So in this case, we're really concerned about the infinite index, or I should say the ending point of infinity, because when we're doing that, that means that you're trying to add up an infinite amount of terms. Well, that's going to take you either a really long time, and you want to know if you're ever going to make it to some value or approach some number, or if it's never going to approach a number and just add up to infinitely large. So the thing is that becomes the difficulty. We don't really, you know, and then we talk about convergence or divergence. So a series is convergent if it approaches some sum, and a series is divergent if it does not, and especially in the cases of infinity, when we're adding things up and we get positive infinity or negative infinity. So again, a series is convergent if it approaches some particular number. When you're adding all the terms up as you approach infinity, you'll get an actual number. Or is divergent if you approach positive or negative infinity, or it can't be, you know, you can't do it in that fashion because it's bouncing around or it's never approaching an actual number. So basically, all we're going to do in this section is just add things up. So that's kind of the beauty of series, is series are just addition. So anything that you can do with addition, you can do with series, but you just have to pay the price with the notation. So sometimes you'll be asked to manipulate things and do things like that with your series, and we can do that very easily. The main thing I would always encourage you to do is to write out your series, write out 4 or 5 terms, you know, 3, 4, 5 terms, and then the new series that you're building that you want to say is the same, you better reproduce the exact same series. So a lot of times, we're asked to change this index right here. Sometimes they ask us to change starting from 1. They might say start at 5 or k plus 1 or, you know, j plus 1 or something like that. So that's just something that we deal with. And we don't really care too much about finite sums. It's something we don't care, but those aren't the hard ones, because if they're finite sums, then they can be added, right? So you automatically know they're convergent because there's a finite number of terms, and you can always add a finite number of terms. It's the infinite sum that is the problem, okay? So let's look at something nice and easy. So does the series n equal 1 to infinity of n converge or diverge? Okay, so what I'm going to do in the beginning, and this will be, you know, just for now, eventually we will have a faster way to do it, but I'm just going to kind of pretend I don't know all this other stuff, and I'm going to try to say, well, what would the first partial sum be? Well, the first partial sum would be 1, so if I plug 1 in there. What would the second partial sum be if I said s sub 2? Well, that means I plug in 1, and then I also plug in 2, right? S sub 3 would be 1 plus 2 plus 3. S sub 4 would be 1 plus 2 plus 3 plus 4. You know, and we could do this all day, right? We could go to S sub 10, and that would be, I'll just tell you now, that'll be 55. And if we wanted, we could go to S100, and that would be 5,050, okay? So This is 1, this is 3, this is 6, and this is what, 10? Okay. So as you can see, does this sum appear to be approaching some particular number? No, it's just getting bigger and bigger. So we would say, since a sub n equals 1 to infinity appears to approach infinity, we're going to say divergent. Okay, so that's basically how you set it up, kind of a slow, tedious way, right? So I'm going to show you one where I already have the values inputted, and I just want to show it to you guys. So let's say, does the series n equals 1 to infinity of 1 over 2 to the n minus 1 converge or diverge? Okay, so we're going to try the same thing. We're going to say s sub 1 equals 1 over 2 to the 0. Well, that would be 1. S sub 2 would be 1 plus 1/2, which would be 3/2, which is 1.5. You'll see why I'm switching to decimals. Normally I prefer fractions, but so this would be 1 plus 1/2 plus, what is it, 1/4? So it's going to be 1.75. S sub 4. So we're doing the same thing as before, 1 plus 1/2 plus 1/4 plus 1/8 equals 1.875. And then this one, you just trust me on, I plug this in and I would get 1.998046875. Okay. And let's do S20. We're going to get 1.99998092651367187. Okay, but would it be safe to say that it appears, so we started here at 1, 1.5, 1.75, 1.875, 1.998, 1.999999809, so on and so on. Would it be safe to say that it appears that it is tending towards 2, right? So we would say the series is converging, to 2. That appears to be the value that is converged to. So because of the sum, all the terms of the sum appear to be converging to a number, that number is 2. So that is what we say the series is approaching. It is approaching the sum of 2. So not only are we looking at, limits and things like that, but now we're actually, we want to find this actual number. We don't just care about convergence and divergence all the time, even though it feels like a lot of this section is just, I don't really care what the answer is, but I just care if it's convergent or divergent. Remember, convergent means it has an approachable finite sum. Divergent means it does not have a finite sum or a value that we can pin down, okay? So we can look at the partial sums to help us. But the problem can become if, what if it takes too long, or how many terms, or what if you want to try to figure out if it's convergent or divergent without a computer system to help you. So what we would do is we're going to learn in this chapter, we're going to learn basically the rest of this chapter is to learn about tests for series, okay, to learn how to test a series for convergence or divergence. Now, these first 2 tests I'm going to show you today, the geometric and the telescoping, they basically deal with 2 series that we actually can find the sum. But in general, most series that we deal with, we just can say convergent or divergent, but we don't actually know what they add up to. We could approximate them, but we don't know the exact value, okay? So the first one we're going to look at is the geometric. This is a big one. Geometric series. Okay, so we have a geometric series and they have the form of n equals 1 to infinity of a r n minus 1. And all that means is if you wrote it out, and you should get used to writing out geometric, because a lot of times they try to fool you and write the geometric in a strange way, but in reality, the nicest thing about series, even though it's kind of the thing that makes them hardest or the most difficult, is that a series can't hide itself. It can't hide from you what it is. It's a pattern, right? It's just discovering that pattern that sometimes can be hard. But a series is just a pattern. It fits a certain form, a way that it's going to be done. So it can't hide. So if you ever have trouble with the series, write out a few terms of it to see what you're getting yourself into. That especially goes for geometric because it's such a nice series. If it ever feels overwhelming, just write out 3 or 4 terms. You should be able to go from there. Okay. So we have a couple rules for geometric series. So you should have learned about these in pre-calc. So if the absolute value of r, and remember r is the common ratio. So basically you're saying that each term is increasing by a multiple of r. So this is technically r to the 0, r to the 1, r to the 2, r to the 3. So you're basically saying to get from one term to the next in the sequence, you multiply by a common ratio. It could be 1/2, it could be 2, it could be 7, it could be 3/4, it could be 0.3. Whatever the case may be, you're multiplying by the same number to generate each new term. Okay, that's the difference between arithmetic and geometric. Arithmetic is changing by addition, and geometric are changing by multiplication. So we really only deal with geometric in this class, not arithmetic. So we have if the absolute value of r is less, you know what, let me write this in red because this is so important. If the absolute value of r is less than 1, then you're good. N equals 1 to infinity of a r to the n minus 1 converges. And not only do we know it converges, we actually know what it converges to, a over 1 minus r. I also a lot of times see a sub 1, basically meaning the first term, okay? So because I didn't write this as a sub 1, you know, they just write a in the formula in your book, but yeah, you could call it a or a sub 1, but what it means is the first term divided by 1 minus r, okay? So then we have if the absolute value of r is greater than or equal to 1, then the series, the geometric series diverges. And then we don't have to worry about the sum because it's divergent, okay? So that's a big, big deal for this class, is knowing convergence and divergence. The geometric will come back in so many different problems, so you really want to be pretty strong at it. So let's say that we have this problem here. So determine if the following series converges or diverges, okay? If convergent, find the sum. So here's the thing. I want you guys to remember this for test taking and everything. We're going to learn like 6, 7, 8 ways to test a series. So basically, it's very important that you understand that most of the series we deal with, we cannot actually find the sum. We cannot actually find the number. We can only say convergent or divergent. Now, here's the thing. If they ever ask you to find the sum, not approximate the sum, but find the exact sum, that probably means you're dealing with a geometric series or with a telescoping series for the most part. An alternating series and then a Taylor series, which can be pretty much everything, we can approximate those to pretty much whatever error you want, but it's still not technically the exact value. So with this, we're saying when I ask you to find the sum, that probably means for the remainder of this course, that means that you're dealing with a geometric or a telescoping. Now, if I said approximate the sum, all bets are off. Everything's different then. But if I ask you to find the sum and it's just straight up the sum, it's probably geometric or telescoping. So here's the series. 2 times 3 over 5 to the n minus 1. Okay. So I want to know if this is convergent or divergent. Okay. So let's first see if it's in the right form. Okay. So this is the form we're looking for. We have our a times the common ratio r, n minus 1. Here's my r right here. Here's r. Here's a. And here's my n minus 1. Oops, and I forgot to tell you, starting at 1 to infinity. Okay, so this looks good. So then we can immediately go over to here and we can say the absolute value of 3/5, which is my r, is less than 1, so convergent, right? And for a problem this easy, that's all you would have to write, okay? So it's convergent, and then I want to know the sum. So I would then say that this equals a over 1 minus r. Well, a in this case is 2 over 1 minus 3/5. Well, that becomes 2 divided by what, 2/5? So this becomes what, 5? And that is the actual sum. So we were able to not only tell it's convergent, but to actually find the sum. I know to you right now, it doesn't seem like a big deal, but that is rare in this chapter. It is rare to find the actual sum, okay? So let me have you guys try one on your own. Okay, so let me give you guys this one, convergent or divergent. If convergent, find the sum. Okay, so I'm going to give you -2 to the n plus 1 divided by 3 to the n plus 2. N equals 1 to infinity. Okay, so first thing you notice is it really isn't in the right form for us. So what I'm going to do is I'm going to kind of go back. It doesn't quite look exactly like this, right? It's not a, r, n minus 1. It's not in like the perfect form. So what I'm going to do is I'm going to fall back on the fact that a geometric series cannot hide from me. If this is a geometric, that means that it should be increasing by the same number each time, or be changing by the same number each time through multiplication. So what I'm going to do is I'm just going to write out some of the terms. Okay. So let's plug 1 in first. So let me just call this my n equals 1. When I plug 1 in, I get -2 to the 1 plus 1, which is 2, so that'd be 4. Oh no, we're starting at 0. I'm sorry. Fix this real quick. We're starting at 0 for this particular problem. Okay, so our index is 0. So it says -2 to the n plus 1. So I plug 0 in for n, and I get -2 to the 0 plus 1, which is just -2. Then I get 0 plus 2 is 2, so this would be 9, right? Because 3 squared. Now I'm going to add the next term. So now we're going to plug a 1 in. So this is n equals 1. So, and again, I'm going really slow. You guys can do this much faster when you write it out. So plug a 1 in. This is 2 squared is 4. Plug there. This would be 27, right? Now it's going to go back to minus because the -2 is going to hit an odd power now. So this is n equals 2. So 2 plus 1 is 3. That would be 8 over, you know what, I can put it right here. 8 over, I'm assuming it'll be 81. Let's plug 2 in there. 3 to the 4th is 81. I'll write one more out just to be thorough. We plug the n equals 3 in. We get 16 over 243. You know, and then it would be minus, and then ... plus, and so on and so on. So it's going to alternate back and forth. Okay, so we've seen some of those problems in the previous homeworks. But I can tell that to go from this term to this term, I multiply by, oops, not 1/3, 2/3. To go from this term to this term, I multiply by 2/3. To go from this term to this term, I multiply by 2/3, right? 8 times 2 is 16. 81 times 3 is 245, or 243. 4 times 2 is 8, right? 4 times 2 is 8. 27 times 3 is 81, so on and so on and so on. So I know that my R is equal to 2/3. Oops, but it's alternating, so actually my R is negative 2/3. So the absolute value of negative 2/3 is less than 1, so convergent by geometric. So in this class, I forgot to write it up here, I got carried away. You always must name the test you're using to prove convergence or divergence. So if you use the geometric, you say by geometric. If you use the comparison, you say by comparison. If you use the divergence test, you say by divergence test, whatever the case may be. So this is convergent. If you do not write this, I will deduct points, okay? So we have R equals negative 2/3. This is convergent. Since it's convergent, we know that it's A over 1 minus negative 2/3. Now all we have to do is A is the first term, so it's negative 2/9. So this will be negative 2/9 divided by, what is that? 3/3 plus 2/3 is 5/3. It'll be negative 2/9 times 3/5. So it'll be what, negative 2/15? And that is our partial sum. We get negative 2/15, okay? So it's not so bad once you kind of get used to it. Let me give you another one. Now, pause the video after I write this one. So determine if this is convergent or divergent, and if it's convergent, find its sum. So kind of following the same rules as before. So let me say that I give you negative 3 to the n minus 1 over 4 to the n equals 1 to infinity. Okay. So pause the video, go ahead and figure out if this is convergent or divergent. And then come on back and we'll do it together. So hopefully you guys unpause the video. And now I want to do something a little bit different just to show you guys. Again, you don't have to do it this way. You could just write out the terms, but you know, I just want to kind of show you that you can manipulate. So technically what I could do is I could do n equals 1 to infinity of negative 3 to the n minus 1. What if I wanted 4 right here to be n minus 1? Well, what if I wrote it as 4 times 4 to the n minus 1? Now, what is 4 times 4 to the n minus 1? Well, wouldn't you just add the powers, right? And that's a 4 to the 1. So that would be 4 to the 1 times 4 to the n minus 1. If you added it, wouldn't you get just 4 to the n? So that's a way I could write it without doing anything. So what I could do is I could write it like this. And now I could take that I could take that 1/4 out of the series. Because remember, a series is just addition. And if you have a 1/4 times every single term that's being added, you could factor that 1/4 out. So I'm going to write the 1/4. You are allowed to take any constant multiple outside of a series with no real harsh penalty. You just got to keep track of it. So this would now become negative 3/4 to the n minus 1. Now, the reason I did that is so I could have it in the right form. So now I know that my R is worth negative 3/4, right? And my A is worth 1, right? Because the 1/4 I'm just going to tack on at the end, okay? So that means the absolute value of negative 3/4 is less than 1, so convergent by geometric, okay? And then we know that it's A, which is 1 over 1 minus negative 3/4. So this will be 1 over 7/4. So this will become 4/7. However, if you recall, but we have to multiply by 1/4, right? This guy right here. Right there, we got to keep track of him. So we're going to say, so the sum is 1/4 times 4/7, which is 1/7. That's our actual sum of this geometric, okay? And remember, again, I said it was convergent by geometric, all right? And you guys could have also chose to write out the terms like I did in the previous one. You didn't have to do it that way. I just wanted to show you that you can always manipulate these terms to try to get things the way you want exactly, okay? So the telescoping is kind of one of the coolest ones, but also kind of the strangest in a way. So I just want to show you guys. So for the telescoping, let's do this. So let's say that we have the series A. Oops, sorry about that. So this is another series that you can actually find the sum of, okay? So with a geometric, they're really nice because we're able to actually find the value that they sum up to. I'm losing a little internet connection, guys. Hopefully I don't drop you. I'm gonna try to plug in my extra Wi-Fi. Let's see how this works. Sorry about that, you guys. Okay, so we have a telescoping series and looks like everything's good. So what we're gonna do is we are going to, it's kind of hard to explain. I think the best way to explain the telescoping is to let you see it. So determine the sum of 2 over n times n plus 1, oops, n plus 2. Okay, so let's say that we have determined the sum of 2 over n times n plus 2, all right? So basically, the problem is that we just want to say, oh, you know, what is this all going to add up to? Well, it's kind of hard to see in this way. So what we're going to have to do is we're going to have to go back to partial fraction decomposition. Do you guys remember in the old chapters, we had 2 over n times n plus 1? So what we're going to do is we're going to go and we're going to do 2 over, so we're going to use PFD. So partial fraction decomposition, we're going to do 2 over n times n plus 2. Right? So this will be equal to A over n plus B over n plus 2, okay? And now if we do this, let's see, we should have 2 equals A times n plus 2 plus B times n. Then we should have n equals -2. So then we have 2 is equal to -2b divided by -2 divided by -2. So we get -1 is equal to b. Okay, and then over here we can say n equals 0. So then 2 is equal to 2a. So then a is equal to 1. So then we actually have this series right here is equal, oops, n equals, let's say 2 to infinity. Let's start at 2 for this particular one. Okay, because you can start at anything you want. So n equals 2 to infinity. Anything you want that is a positive integer. I guess you can also start a series at 0 as well. So I guess just 0 or whole numbers. So the thing is that I'm going to rewrite my new series 1 over n, and we said b was -1. So this will be -1 over n. Oops, n plus 2. Sorry about that. Sorry, I'm getting a little sidetracked. I'm trying to worry about my internet if it's working. Okay, so we have that. Now the thing is that when I go ahead and do this problem, it's still kind of hard to tell what's going to happen. So what I think I should do instead is I should write out some terms. So I'm going to write out these terms just to see what's happening with this series. So I'm going to plug 2 in. So this will be 1 over 1/2 minus 1/4, right? That's the first set. That's for n equals 2, right? Now I'm going to plug in the next one. I'm going to say plus, remember this is a series, so we're adding, so this will be n equals 3. You know what, this is too big. I'm going to run out of room. So let's do 1/2 minus 1/4 plus, now I'm going to plug 3 in, 1/3 minus 1/5, plus I'm going to plug a 4 in, 1/4 minus 1/6. I'm going to plug another one in. Let's go, what do you want to go? S sub 6. So this would be n equals 2, n equals 3, n equals 4. So plus 1/5 minus 1/7 plus 1/6 minus 1/8. So this is n equals 5 and n equals 6. Okay. So hopefully you guys see that. So that's the 6 partial sum. Okay. So what you notice is that you see this 1/4 is positive and this 1/4 is negative, so they would technically cancel. You see this 1/5 is negative and this 1/5 is positive, so they would technically cancel. This 1/6 is negative, this 1/6 is positive, so they would technically cancel, right? So the only thing left standing would be 1/2 plus 1/3 minus 1/8. So the 1/2 and the 1/3 would never get touched. What if we went to S sub 8? What if we went to S sub 10? The 1/2 and the 1/3 would never get touched, right? But what's left standing is this 1/8 right here, okay? Now, what is the relationship of 8 to the 6th term, the fact that we're on n equals 6, right? I guess not the 6th term, but n equals 6. Well, it's 2 bigger. So this is S sub 6. But what if I wanted to find... let me see. I could rewrite this as S sub 6 is equal to 1/2 plus 1/3 minus 1/6 plus 2, right? And this is the 6 from this guy right here. That's a way I could describe it. Now the thing is you guys understand that if I went to the next term, the 7th term, then it, or S sub 7, I should say, the 7th partial sum, it would be, what would we get? The 1/9 would not go away, right? Because it'd be 7 plus 2. That would be the value that didn't cancel. If we went to the 20th term, right, it would be 1/22. If we went to the 50th term, it'd be 1/52 that would be left standing. Everything else would always cancel. So the telescoping to me kind of eats away at itself until there's only a little bit left. So here, what if I wanted to go to S sub k? I don't know what term that is, but just whatever partial sum you want to stop at. Well, that would be 1/2 plus 1/3 minus 1/k plus 2. So if we stopped on 50, it would be 1/52 because we would do 50 plus 2, okay? But technically, this goes to infinity. This is an infinite series. So we're going to say the only way I know how to deal with this is to find the limit as k approaches infinity of S sub k, which is equal to 1/2 plus 1/3 minus k plus 2, which equals, oops, let me write this cleaner, equals the limit as k approaches infinity of 1/2 plus 1/3 minus 1/k plus 2. Now we know that this will be 1/2 plus 1/3 plus, oops, minus 0, because this term right here, as you approach infinitely large, will become 0. So then our final answer is actually just 5/6 if we add these up. Kind of a rough one. The telescoping is kind of strange, to be honest with you, the way it kind of works. The main way you can recognize a telescoping is if you have a denominator that's factored. There's other ways that's not always the case. I've seen some with natural logs as well sometimes. But if there's a way that you can factor the denominator, normally then you have to go into partial fraction decomposition. And just so you guys know, the partial fraction decomposition will be like a very easy one like this one, nothing too complicated. This is a standard test type question just to show me that you know how to do it. So needless to say, this would be something you're going to see on the exam, okay? And you do have to show me your work, so must show this. You have to show me that, and then you must show me the limit. The limit is essential, okay? You have to show that you know that since this is approaching infinity, S sub 6, S sub 10, S sub 1,000 doesn't matter. You need to approach infinite amount of terms, okay? So that's a telescoping, okay? Let me double check something real quick. Let me just find this in my notes really fast. Okay, so it looks like your book actually kind of holds off on that. They focus more on the test for divergence. But let me come back to this. Let me give you a couple basic facts about series. So remember, the big thing is that series are just additions. So there's a lot of things that you can do. So, given that the series A sub n equals A, and the series of B sub n equals B, where A and B do not equal, plus or minus infinity. So if C is a constant, then we have the following. The series A sub n plus or minus B sub n equals the series n equals 1 to infinity of A sub n plus or minus, I was reading the wrong thing. So this would be A plus or minus B, okay? We also have this fact, C times A sub n is equal to C times the series A sub n equals C times A. Okay, so what this is basically telling you is that you can split these two series. If you have a series, and again, I need you to understand there's kind of an embedded little idea here, okay? So they're telling you that it equals A and this one equals B. That means they're already convergent. They're telling you how much they add up to. So this means they're already converging to A and to B respectively, whether A is 75 and B is 20, they're saying they're convergent. So you're only allowed to do this because they're convergent, okay? To some value. If C is a constant, then this happens. So right here, they're basically saying, if you're taking the series of these two sequences, A sub n and B sub n, right? You can split them and you can say that the sum of this guy plus the sum of that guy is legal to do. You are allowed to say that, okay? So whatever his sum was plus whatever his sum was, you can just do it like that, okay? They just want to let you know that that's okay, but they both had to be convergent sums in the first place, okay? So that was kind of a hidden meaning. Now this one says if you have a constant times this sequence, and then you're going to work with the whole series, what you can do is you can just move the constant outside, find the series itself sum, and then multiply the constant back together. That's exactly what I did up here with the 1/4. So right here, that's what I did. I pulled the 1/4 out and brought it back in. So this is just kind of some facts about series that we can go over, or that we're going to be using throughout this section. Okay. Okay, so I think that's going to be it. The next section will be on the test for divergence and the integral test, and that will be 10.4. Thanks for watching, you guys. I will see you in class or in the next video.